Hey everyone, so let's see, what we've been studying is irreducibility over Q, and we have two main results so far. So the first one, I don't remember what, I want to say 23.9, I think, but it doesn't matter. So it goes like this. So if we take a polynomial with coefficients in z, so if this polynomial is irreducible over z, then the polynomial is irreducible over Q, right? So that then reduces the question of studying polynomials with rational coefficients to coefficients over the integers. So there's the first of our important results. The next one was the mod P test, right? So if you take a polynomial with integer coefficients, so if this polynomial is non-constant, and in fact, let me phrase it a little bit better. So let's let f of x be an integer polynomial that's non-constant. So let this be non-constant. And so then it goes like this: if the degree of the polynomial when you reduce mod p is equal to the degree of the original polynomial. So if when you reduce mod p the degree does not go down, and f bar of x is irreducible over zp, then f of x is irreducible over q. So when this works, this is nice, right? If you can find a choice of prime p, remember this prime has to be p, so that the polynomial that you get when you reduce all the coefficients mod p is irreducible over zp, then you're allowed to conclude that that polynomial is actually irreducible over q. Now, what I'd like to do is a couple more examples of this. And so the first example, so let's let f of x equal, so this is going to be 3/7 x to the, sorry, I can't even read, my eyes are getting bad here, 3/7 x to the 4th, is that what it was? Yeah, x to the 4th, yeah, minus 2/7 x squared, plus 9/35 x plus 3/5. Okay, so here we have a polynomial, right, with rational coefficients, and what we want to do is I want to show that f of x is irreducible over q. Now, the first thing that I want to do is make use of our result right here, that I want to really work with integer polynomials. And so what I want to do is clear out the denominators, right? So I'm going to multiply by 35, right? So then we have, or so consider the polynomial 35 f of x, which is going to be 15 x to the 4th minus 10 x squared. Oh, so I'm sorry, that should say 9/35 x right there. So then it'll be plus 9x plus 21. Right now we have a polynomial with integer coefficients, and we should observe that if we could factor f of x, then we could factor 35 f of x. And so, if we can show that 35 f of x is irreducible over q, then we can conclude that the original f of x is also irreducible over q. All right, so that's the idea, is anytime you have a polynomial with rational coefficients, you can clear all the denominators out, work with a polynomial who's with integer coefficients, and then we can make use of tests like, right, the mod p-test. Okay, so now what we want to do, all right, so let me just say that. So it suffices to show that f of x is irreducible over z. All right, if I can do, 35 f of x is irreducible over z. If I can do that, then we know that the original polynomial is irreducible over q. So now, the idea, this is an example of using the mod p-test. So what I'm going to do, and this is typically what you do, is you try starting off with small prime. So our smallest prime is 2. Let's try mod 2. So if it's kind of weird notation here, but in fact, it's okay. So let's do it like this. So let's write g of x equal to 35 f of x, because I want to bar this. I just don't want to have this weird notation where I'm barring 35 f of x. So I'm going to bar g. So then g bar of x is equal to, so let's see, if we reduce mod 2, I'm going to get an x to the 4th plus x plus 1. All right, reduce mod 2, here's the resulting polynomial. Now, let's see, we want to show that it's irreducible over z2, which means that we want to show that it cannot factor as a degree 1 times a degree 3 or as a degree 2 times a degree 2, right? We've got a degree 4 polynomial. So the first thing I need to do if I want to show it's irreducible, I'm going to show that it does not have a degree 1 times a degree 3 factorization over z2, which means that I just need to show that it does not have a 0 in z2. So since g bar of 0 equals 1 and g bar of 1 also equals 1, we see that g bar of x does not have a linear factor. Right? So that rules out the possibility of a degree 1 times a degree 3 factorization. Now I need to show that it does not factor as a degree 2 times degree 2. Okay, so let's see. What we need to do is identify the possible quadratic factors. So the quadratic factors are quadratic polynomials. And I should say the monic quadratic polynomials. Oh, no, I guess it doesn't matter in this case. Okay, the quadratic polynomials in Z2 bracket X are, so let's see, there's going to be x squared plus 1, x squared plus x, and x squared plus x plus 1. All right, so there's exactly 4 quadratic polynomials in Z2 bracket X. And here's what you want to notice. The first 3 are reducible. Meaning that each one of them factors as a degree 1 times a degree 1. So if any one of these 3 was a factor of g bar, that would tell us that g bar has a 0 in Z2, but we already know it doesn't. So the only polynomial that we have to consider as a potential factor is the irreducible one. Okay. So there's only one thing to try. So let's say it like this. So note that the first three are reducible over Z2. So we only consider the last polynomial in the list. And so what I want to do is show that this polynomial right here is not a factor of g bar of x. And the way to do that is long division. So I do x squared plus x plus 1 into g bar. And that was, let's see, x to the fourth plus 0x cubed plus x squared. Who is it? No. Is it 0? Oh, yeah, 0x squared plus x plus 1. Now, x squared goes into x to the fourth one time. Multiply this out, we get x to the fourth plus x cubed plus x squared. Subtract. That's going to give us a negative x cubed. And remember, in Z2, subtraction and addition are the same thing. So this is actually an x cubed plus x squared plus x. X squared goes into this one, into x cubed, it goes in x times. So this will be an x cubed plus x squared plus x. Subtract, we get 0, bring down the 1, and so we have a non-zero remainder, which means that this polynomial is not a quadratic factor of g bar. So since x squared plus x plus 1 is not a factor of g bar of x, we conclude that g bar of x is irreducible over Z2. It didn't have a linear factor, it didn't have an irreducible quadratic factor, therefore it cannot factor. Conclusion, or so let's say therefore. G bar, f of x is irreducible over Q. And I want to do one more example of application of the mod P test, and then we're going to learn a new test. So next one here, so now we're going to do degree 5. So f of x equals x to the fifth plus 2x plus 4. And what I want to do is show that f of x is irreducible over Q. And so what I'm going to do is I'm going to start off with a mod 2 test and see what happens. So for mod 2, what do we get? We get f bar is equal to the x to the fifth, right? Well, obviously it's reducible over Z2. So what that tells us is that the mod 2 test fails. It gives us no information, right? And so, so now we move on to mod 3. And so in that case, f bar is going to be x to the 5th plus 2x plus 1. All right, so now what do I need to do? Well, for a degree 5 polynomial, it could factor as linear times degree 4, or it could be a degree 2 times a degree 3. And so if we can rule out both of those, then we can conclude that our polynomial is irreducible over Z3. So first let's check linear factors. And so we do it like this. Since f bar of 0 equals 1, f bar of 1 equals 1, and f bar of 2, all right, 32 plus 4 plus 1 gives us 37. Mod 3 is also 1. And so, let's finish the sentence here. We can say since that and that, we see that f bar of x has no linear factors in Z3 bracket x, right? So that tells us it does not factor as a degree 1 times a degree 4. Now we need to see or show that it can't factor as a degree 2 times a degree 3. So recall from last time, the irreducible quadratics in Z3 bracket x are, and remember there are exactly 3 of them, so those are the only ones that we need to rule out, and let me just write them down here. So there are x squared plus 1, x squared plus x plus 2, and x squared plus, is it 2x? Yeah, 2x plus 2. So what we need to do is long division, divide each of these 3 into this polynomial. If we can show that none of them divide cleanly into it, then we can conclude that f bar is irreducible over Z3, and that will then lead to the conclusion that that the original f is irreducible over Q. And so I'm just going to do, let me just pick one of them. So use long division to show that none are factors of g bar of x. I mean, I don't know if you want to see me do long division. All right, let me just do one of them. So I'll do the middle one here. So x squared plus x plus 2 divided into f bar looks like this. X to the 5th plus, I'm going to run out of room on it. You do it over here. X to the 5th plus 2x plus 1. So x squared plus x plus 2 divided into x to the 5th plus 2x plus, oh man, it was 2x plus 1, right? Of course I erased it and there's no one here that can tell me. Yeah, plus 2x plus 1. Okay, so it'll be plus a 0x to the 4th plus 0x cubed plus 0x squared plus x plus 1. X squared goes into x to the 5th, x cubed times, multiply that out, we get an x to the 5th plus x to the 4th plus 2x cubed, subtract. That's going to give us a negative x to the 4th, which is the same as 2x to the 4th, minus 2x cubed, which is the same as plus x cubed, and then we have plus 0x squared. X squared goes into 2x to the 4th. 2x squared times, multiply it out, 2x to the fourth plus 2x cubed plus 2x squared, subtract. That will give us a negative x cubed, which is the same as 2x cubed, minus 2x squared, which is the same as plus x squared, and then we bring down the x. And then this polynomial goes in 2x cubed times. 2x times. Then we'll get a 2x cubed plus 2x squared plus x. Subtract. And that's going to give us a negative x squared, which is 2x squared, plus 0x. Bring down the 1. And then this is clearly not going to go in cleanly, but let's just finish it off. So plus 2. So that'll be a 2x squared plus 2x plus 1. Subtract, and we get a negative 2x, which is x. Non-zero remainder tells us that this polynomial is not a factor of f bar of x. Oh, and I'm sorry, I called it g bar, didn't I? When it's really f bar. Okay, so once you've done that then, so there's 2 more long divisions that you need to do, and then you say conclude that f bar of x has no quadratic factors. Therefore, so by the mod 3 test, f of x is irreducible. Over Q. So we've seen a few examples now of applying the mod p test, and the mod p test is nice as long as you don't have to go too high with your choice of prime number, and as long as you're not considering a polynomial of very high degree, right? Because the number of long divisions that you'd have to consider is going to go up as p goes up. I don't know why I have a z5 there written there. Right. So as the prime p goes up, the number of polynomials you have to consider goes up. Also, as the degree of your polynomial goes up, the number of polynomials that you'll have to do long division with also goes up. So my point is the mod p test is practical for small degree polynomials as long as it doesn't, as long as it doesn't go up too high. And you'll see in your homework problem that there are polynomials for which the mod p test fails for every single choice of p. So what we're about to learn now is a much more advanced test. When it works very easy. You really don't have to do any work. You can kind of just eyeball the solution. And this is pretty famous. This is probably the most famous of the irreducibility tests. And this one, so this is 23.12, and it's called Eisenstein's criterion. So let's take a polynomial. So let's let f of x equal a0 plus a1 x plus dot 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 plus an x to the n be a polynomial with integer coefficients, and we need a prime number, so let's say and let p be prime. Now if p does not divide the leading coefficient, right, the a sub n, p divides a0, p divides a1, all the way up through so p divides a sub n minus 1. So p does not divide the leading coefficient, but divides all the other coefficients, and p squared does not divide a0. Then f of x is irreducible over Q. So it's kind of a curious criterion. That turns out that it's true, and we're going to see in the proof that we'll see why all of these conditions work, or why we need all these conditions as we go through the proof. Okay, so what we're going to do is, suppose that the hypotheses hold, but that F actually is reducible over Q. Right? So suppose the hypotheses hold, but that f of x is reducible over Q. Now we know if we have an integer polynomial and it is reducible over Q, then it's reducible over Z, right? So by, that's, I think it's 23.9. Yeah. So by 23.9, there exist a couple of polynomials. So this would be, say, g of x and h of x in z bracket x, with the degrees both strictly less than the degree of f. So with degree of g of x and the degree of h of x strictly less than the degree of f of x, which is n, and, or let's say such that f of x factors as g of x times h of x. Now I need to write these polynomials out, so let's write g of x. It's going to be b0 plus b1x plus dot dot dot, and we're going to go out to degree k, so that'll be a b sub n x, b sub k x to the k. And let's write h of x. That's going to have c coefficients, so c0 plus c1x plus dot 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 plus c sub, I think I use an m here, c sub m, yep, x to the m. Okay, so now if you multiply these two polynomials, we're supposed to get f. In particular, when you multiply the constant coefficients, right, that's going to be a b0 times c0, that's going to give us a0. Right, so then a0 is equal to b0 times c0. Now, let's see, what do we know? We know that p divides a0, but p squared does not divide a0. So we know that p divides this product right here, which means that p needs to divide one of the two coefficients. But because p squared does not divide this product, it can't divide both. Right? So since p divides a0, but p squared does not divide a0, we know that p divides b0, or p divides c0, but not both. And so it doesn't matter which one. I'm just going to assume that it divides b0 and that it doesn't divide c0. So let's just assume, without loss of generality, that p divides b0, but p does not divide c0. This is sort of a standard abbreviation for without loss of generality. All right, so WLOG. Now, so now what? Oh, right. So the next thing, so since let's see, what else have we assumed? We have assumed that p does not divide the leading coefficient. So since p does not divide a sub n, now how would we get a sub n? You would multiply bk times c sub m. So since p does not divide a sub n, p does not divide the product bk times c sub m, which tells us in particular that p does not divide b sub k. So since p does not divide a sub n, we have p does not divide b sub k. All right, so now what do we know? Okay, so we know that p divides b0. P does not divide b sub k. So if you look at this polynomial, it divides the 0th coefficient. It does not divide the kth coefficient. So, you know, p divides b0, but maybe it doesn't divide b1. Maybe it does. Maybe it divides b2, maybe it doesn't. And so you can go along the line. At some point, there will be, right, we know it divides b0, there will be a first coefficient that is not divided, or that p does not divide. So let's let, so this is going to be some number t between 1 and k. So let this be the least such that p does not divide b sub t, right? As you go along this list, you know that p divides b0, and so at some point as you go down the line, because it doesn't divide bk, at some point as you go down the line, it will not divide some coefficient, so we're going to pick the first time that it happens. It's possible that it divides all of them all the way up to k plus 1, and just doesn't divide the last one. That's fine, then t equals k. So we just want t to be the least such. So now let's look at the coefficient a sub k. So now a sub k is going to be obtained as, so that'll be a b0 c sub k plus b1 c sub k minus 1 plus dot 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 plus b sub k c sub 0. Now, since k is strictly less than n, right, we know that p divides a sub k. So we have p divides a sub k. Now, what? All right, so now we have, so let me think here. Oh, crap. I'm sorry. I don't want to look at a sub k. I want to look at a sub t. I'm sorry. Oh, that sucks. A sub t. So that's going to be a ct. I'm sorry. You're going to have to change all of this stuff. That sucks. And that's a t right there. And so since k is less than n, yeah, when I looked at this, p divides a sub k. So this is, we have, yeah, sorry, that's a t there right there. Sorry, all those k's, including, yeah, sorry, that should be a t also. Sorry, every k needs to change to t. Sorry, I just blew, this is such a fun proof and I just blew an important part there. So, I'm sorry. What did I do right here? I look at the tth coefficient, right? T is this least such that p divides or does not divide. I write out what a sub t looks like. It looks like this. Now we know that t is strictly less than n. Why is that? Well, because t is less than or equal to k, and we know that k, right, the degree of g, is strictly less than n, right? And so our assumption is that p divides a sub t, right? P divides all of the coefficients from a0 all the way up to a sub n minus 1. So in particular, p divides a sub t. So now we have what? Well, p divides a sub t, and I don't know why I'm repeating myself here, but p divides a sub t, and p divides, so let me think here. P divides b0, p divides b1, all the way up to p divides b sub t minus 1. And so, p divides a sub t, put this in parentheses here, a sub, actually I'm going to put it in square brackets. P divides a sub t minus parentheses b0 c sub t plus b1 c sub t minus 1 plus dot 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 down to b sub t minus 1 c sub 1. All right, so what just happened? We know that p divides that guy right there. We know that p divides each of these numbers, right? b0 up through b sub t minus 1, which means that p is going to divide each of those pieces right there. So p divides this summation, or this difference right here. But what is this difference? This difference is going to be bt times c0. So this is equal to so p divides bt times c0, but p is a prime number, so since p is prime, p divides bt, or p divides c0, but we know that it doesn't, all right? All right, t is the least such that p does not divide it. Okay, so this is a contradiction. What caused that contradiction? The assumption that we could factor in the first place. That proof is awesome. I wish I wouldn't have screwed up my subscripts right here, but hopefully you see where the mistake, I mean, it's just, I wrote K's instead of T's. I wish I wouldn't have, but hopefully now you can see this is a cool proof, right? This is fun. And now let's see how this theorem works in action. So as an example, let's look at so this is going to be the polynomial 3x to the 5th. So f of x equals 3x to the 5th plus 15x to the 4th minus 20x cubed plus 10x plus 20. All right, so what do we want to do? If we can find a prime that divides all except the leading coefficient, and whose square does not divide the constant coefficient, then we're done. We know that this polynomial is is irreducible over Q. Right? So since 5 does not divide 3, 5 divides 15, 5 divides minus 20, 5 divides 10, 5 divides 20, and 5 squared does not divide 20. f of x is irreducible over Q by Eisenstein. So when Eisenstein works, there's really not much work to do, right? I mean, but sometimes it works, sometimes it doesn't. If you can find a prime that satisfies those conditions, then without any real arithmetic, you can just make a conclusion, irreducible over Q. Okay, so we're going to start a new chapter, I think, next time. Yeah, okay, so we'll see you then.